In the previous session, we are discussing about this diffusion phenomenon, right? Diffusion of carriers in semiconductors, right? And then we have derived this Einstein relation, the famous equation. So the importance of this equation is like here we are relating two different parameters, right? We have dn, that is diffusion coefficient, and then we have mu n or mu mobility, right? So the importance is here we are relating the diffusion coefficient and or diffusivity and mobility, right? So diffusivity and mobility. And as you can see that this kt by q in between this factor, right, it is constant, right, for a particular temperature. So we can say that dn is proportional, or d is proportional to mu, right? Diffusivity is proportional to mobility. So as the mobility increases for a carrier, the diffusivity also increases. I mean, it's normal way we can feel it, but mathematically also we can see that. And Einstein, he first derived this relation, and that's why you call it as Einstein relation. Now, so we learned about this diffusion current, and then the previous session before this, so we learned about drift current, right? So the total current in a semiconductor, it depends on both, right? So if you want to write down the total current density, basically we are talking about, right? So total current density, let's write it as J for electron. So it will have two components, right? So we'll have drift, which is governed by electric field, and we will have diffusion, right? So diffusion is due to the concentration gradient, right? So J drift we already calculated, right? For electron it was Q mu n, then n electron concentration and electric field value, right? Plus J diffusion, just now we calculated, it is Q dn dx, right? So this is for electron, and if you this is the electron current density. We'll just write it up a little bit. Electron current density, right? So we are, and then we have holes also in the semiconductor, right? So the hole current density will be, so we define it as Jp, right? So for holes it is again drift Q mu P, and hole concentration is P into E minus Q dP dP dx. So here you can see that we are using a negative sign for holes, right? Hole diffusion current, because for the holes, if the concentration, let's say here we have more number of holes in this region, and then let's say this region we have less number of holes. Okay, so the concentration gradient, if you see in this direction, so this side is higher to lower, so gradient or dp dx in this direction, it will be negative, right? It is decreasing in this direction, right? And the holes will flow from in this direction only. Let's say this is our positive x-axis, right? So you can see the hole concentration is negative, but the current in this direction will be positive, right? Because the direction hole goes, current also goes in the same direction, right? so it's positive. So you can see there is a contradiction, right? In the positive x direction, whole concentration is negative, but current is positive. But if you consider electron situation, it is again different, right? Because in electron, if you just flip the situation, so if you consider these are electrons, then the same situation, the electron concentration in the positive x direction is negative, but the current, the current will, electron will flow from positive x only, but current direction will be opposite, right, for electron. So we'll have a negative sign there. So these two negative will make this quantity positive, right? But for hole it is different, because the whole flow direction and current direction is in the uh, same way, right, in the same direction. So that's why this negative sign comes. Hope it's clear. Okay. So we have got whole current because of electrons and current because of the holes, right? Or current density basically measured here. Now, if you want to have the total current, so total current density, total current density, you can guess it, right? It will be sum of electrons contribution and hole contribution, right? So this equation is very important, because whenever we try to understand any semiconductor device, we need to see their current equation, right? So later on we will again break into different, we'll go inside this, like for diode or transistor. So sometime you will see that electron current density is more, in some junction hole current density is more, and sometime we will notice that the contribution coming from drift is more than diffusion. In some junction diffusion contribution is more than drift. So it contributes basically four components, right? We have drift for electron, diffusion for electron, drift for hole, drift for holes, and diffusion for holes. So we'll see all these four parameters. They are very extremely important, these equations, in the later on also. We'll see that one. But for time being, we'll just go to little bit more on basics, like the carrier generation recombination. So this part we'll cover of today. Okay. So carrier generation and recombination. Okay. So as we already know that at thermal equilibrium, uh, at thermal equilibrium, we know that N into P equals to Ni square, right? That is the concentration of electron, and multiplied by concentration of hole is equal to the square of intrinsic carrier concentration, right? Now this is only at thermal equilibrium, and when you use the device, they are not anymore in thermal equilibrium, right? When you are, let's say, a diode, so you are not using the diode, it is just simply lying on the table, fine, it's in thermal equilibrium. Let's say there is no light falling on it, it's in thermal equilibrium. Now when you start using it, maybe let's say it's a solar cell, right? It could be a solar cell. So when you shine light on this solar cell, again it's a PN junction, we are talking about PN junction solar cell. So when you shine light on the solar cell, or in the junction, basically PN junction, so what happens is there will be some excess carrier, right? Now in this situation, when lights falls on the semiconductor and there is a absorption probability, then the system is not in thermal equilibrium, right? and this equation will not hold also. And at that situation, when there is a excess uh, carriers in the system, then this N and P, or the concentration of electron and holes, will be much higher than its intrinsic concentration, right? Because we are considering that there is a generation possibility, right? So uh, let's say a simple semiconductor, we are not talking about even a junction, a simple piece of, let's say, gallium arsenide, right? Now if you shine with light, and if this h nu is greater than the band gap of this gallium arsenide, so these photons will get absorbed, right? And there will be generation of electrons and hole pairs within the semiconductors, right? So in this situation, obviously the electron concentration is higher than thermal equilibrium, and hole concentration also higher. Now we need to understand this situation, that uh, when there is the excess carrier, and this condition always holds, right? Whenever we try to use any semiconductor device, there is excess carrier in the system, or the system is in thermal non-equilibrium. It is a non-equilibrium state, right? So how can you create excess carriers? So one I already described. One is via optical excitation, right? Like, for example, I given solar cell here. It could be a photodiode also. They work on these principles. Okay, and then there could be another way of excess carrier, or this is also known as excess carriers, or it's called carrier injection, because we have excess carriers, so also called as carrier injection. So it can be if you forward bias a PN junction, right? In that case also we inject some carriers from one side to the other, right? We'll come to the details of carrier injection, but just giving you an example where we have these excess carriers or carrier injection phenomenon, right? Forward bias, this could be diode, transistor, in this situation, right? Now when there is an excess carrier, the system is unstable, right? So for example, this gallium arsenide case, so we shine light on the semiconductor, there is a generation of excess electron holes. Now if you switch off the light, or if you turn off this radiation on it, so what will happen? This excess carrier, do you think it will remain in the system? No, right? Because they will try to again achieve the thermal equilibrium, because our external perturbation or external, the source of energy is stopped. So the system will attain again at thermal equilibrium, right? So if you stop this h nu or this radiation, then the system will again try to attain at thermal equilibrium, right? So it will again uh, achieve equilibrium. Okay. So how will it achieve thermal equilibrium? So those excess carrier has to recombine each other, right? So whatever the electrons and hole generated, they will recombine to each other, or they will annihilate basically, and whatever the excess carriers, they will not be present anymore. Only the thermal generated carriers will be present, right? So again, that equation NP equal to Li square will hold good after some time. So uh, so this is happening, or the reverse process. So first process was here, it was a generation, right? Generation process. And now when you stop this light emission or these photons, then we'll have recombinations. Okay, now one more thing, even if we keep shining the light, then also the recombination takes place, right? So let's say we are switching on this H nu, or we are shining the light constantly on that semiconductor. Then what happens? First generation takes place, and then when there is an excess carrier, they will recombine. Right? The recombination rates also increases, and again within the light, or I mean, with light also, the system will achieve an equilibrium condition where the generation rate will be equal to recombination rate. Right. So we'll derive those conditions. Now let's talk about little bit of recombination. So generation, we got to know with these two condition we can create generation. And now talking about recombination, so there are different types of recombinations in semiconductor, right? We'll learn that. Recombination. So in recombination, what happens? One electron and one holes, they basically recombine or annihilate, right? And the excess or whatever the energy they had, they can release uh, into a radiative transition, or there could be two possibilities, right? The excess or whatever the energy the electrons and holes had, they could recombine radiatively or non-radiatively. So there are two possibilities, radiative and non-radiative recombinations. Right? Now, a radiative recombination, why do you see? If I ask you, we already covered this in the basics of semiconductor. So why do you see radiative recombination? Which type of material?
So direct band semiconductor.
Exactly. So radiative recombination, it takes place in direct band gap semiconductor, right? And this also called direct recombination, because it's a band to band transition, right? There is no momentum into this picture, right? There is no change in momentum. You remember this diagram. So you have valence band, conduction band, and if this bottom of this conduction band and top of valence band, they are in the same line, so we have this kind of direct recombination or radiative transition, right? So whenever one electron comes from conduction band to valence band and recombine, the excess energy, it comes out as a photon, right? So this is radiative, and non-radiative happens normally in indirect band gap semiconductor, right? So this is for indirect band gap semiconductors. So indirect band gap again, so it involves momentums or photons, and most of the time the energy it emits as heat into the lattice, right? We don't get photon. I mean, the probability is very low. Okay. So yeah. Now let's define few parameters, and then we try to see mathematically that how this generation and recombination rate they are correlated. Okay, so let's define generation rate. So for that, I'll just give an example, so it will be very easy to follow up. Okay, so let's take gallium arsenide again. So gallium arsenide, we have this conduction band, sorry, this is valence band, right? And this is the conduction band. And so energy, let's say it is EV, and the conduction band energy EC, right? And now at thermal equilibrium, okay, at thermal equilibrium also this generation recombination takes place, right? So there will be some electron due to this thermal energy at even at room temperature, some electrons break the covalent bond and become free, or it will reach to the conduction band and it will create a hole basically in the valence band, right? So how fast this process takes place, or this process is called basically generation, right? Carrier generation. Now if you consider the rate of this process, so we'll define one parameter called carrier generation. So we define as GTH because we are talking about at thermal equilibrium. Right now we are at thermal equilibrium, okay? So at thermal equilibrium, this is the rate. Some electrons will break the covalent bond and reach the conduction band, and it will create a hole in the valence band, right? Now also the opposite process takes place, right, at the same time. So some of the electron again it recombines with the holes, right? So this is GTH, and the recombination rate, let's say it is RTH. So this is RTH at thermal equilibrium. Now we know very well that at thermal equilibrium these two rates has to be equal, right? Then only the system will be at thermal equilibrium, right? And at that condition again this Pn equal to Ni square, this relation also holds good, right? So the carrier generation rate, okay, let's define this parameter. So how do you define it? Obviously it is carrier generated per unit volume per second, right? So we'll just write it off so we'll not forget it. So generation rate, it's like number of carriers. So first I'm trying to write the generation rate. Yeah, we are writing this parameter here. Carrier generation unit volume, so we'll put centimeter cube and per second. And similarly carrier recombination rate is number of recombinations per unit volume per second. Okay, now having said this, so this is at thermal equilibrium. Recombination will depend on what? The number of electrons present in the conduction band, right? If they are more, recombination rate will be more, right? And number of carriers or number of holes in the valence band, right? So it depends on those concentration, right? If there is no electrons, there is no possibility of recombination, right? Similarly, there is no holes in the valence band, there is no possibility of recombination. So we have to have both electrons in the conduction band and holes in the valence band, then only recombination takes place, right? So to put it in a mathematical way, this recombination rate, okay, now we are talking about the recombination in general. We are not talking about at thermal equilibrium right here, right? We put RTH, it's thermal equilibrium, but now we're talking about in general recombination. It could be at thermal equilibrium, it could be at a non-equilibrium condition, right? Like the light, maybe there is a carrier injection in the system, but this recombination rate is proportional to small n, right? Small n we already know, it's the concentration of electron in the conduction band, right? And also R is proportional to the concentration of hole in the valence band, right? It's all probability, right? So if you combine these two equation, and put a constant, proportionality constant. So R is basically beta into N into P. So the recombination rate R is recombination rate or rate of recombination. N and P I'm not writing again and again. Okay. Okay. So beta we defined. So beta is a proportionality constant. Now at thermal equilibrium, again, if you go, or when the system is stable, then the total recombination rate will be equal to again total generation rate. Even when there is when let's say there is a fixed amount of light falling on the semiconductor, so again they will be equal. Now yeah, now we'll take a special condition, right? We'll talk about only n type semiconductor. If you consider a n type semiconductor, then for a n type semiconductor we define it as at thermal equilibrium. So generation rate at thermal equilibrium equal to recombination rate at thermal equilibrium is equals to beta. So it is beta NP, right? Now we define it is like this: beta N N0 P N0. So let me explain this notation. So whenever in this, we'll be using this subscript a lot, this type of subscript. So whenever in the subscript, the first term, in this kind of subscript, the first term defines the type of semiconductor. Okay. So it's defined as type of semiconductor. So in this case, we are talking about N type semiconductor. So we put N, even for the whole concentration. And 0, or the second term, it defines about the condition. So 0 defines at thermal equilibrium. Okay. So I hope this is clear now. So we have type of N type semiconductor. So obviously this N0 will be much greater than P0, right? Because it's a N type semiconductor, right? So similar way you can write it for P type semiconductor, right? So it will be P0 into N P0, right? For P type semiconductor. So this is at thermal equilibrium. Now let's try to correlate these equations at non-equilibrium condition. Okay, so we'll just move to one non-equilibrium condition. Not non-equilibrium, we'll take a condition where there is some carrier injection. So or we call it as excess carrier. So when there is some excess carriers, we'll see how this recombination and generation rate, how they are correlated. Okay, so for this we'll take an example of gallium arsenide. Okay, so let's draw its band diagram. So we have valence band, and we have the conduction band. This is the band energy, right? Bandage energy. Now at thermal equilibrium, sorry, let's talk about first the generation rates, right? So excess carriers. So if we shine light onto this gallium arsenide, so we are basically supplying some external energy to this system, right? Now when you supply external energy, and again this condition we have to maintain, this H nu is more than the band gap of the semiconductor, so these photons will get absorbed, and because of this there will be a generation rate, right? This generation rate, because of this light, So let's talk it as GL, or generation rate due to the light, right? So GL is generation rate due to light. Now this GL, again, it depends on the light intensity, right? If you shine with higher intense light, GL will increase, right? And also the wavelength we shine, right? So it has to be greater than the band gap, then only it get absorbed. Now there is also thermal generation. Along with this, we have also thermal generation, right? Which is always present if we are at a particular temperature, right? So GTH is constant, always there, but in top of it, on top of it, we have this light generation. But we have, so this system is now only generation will not be taking place, right? There will be recombination also. So when there is carriers or there is electrons in the conduction bands and holes in the valence band, recombination also takes place parallelly, right? And this system will attain to an equilibrium condition, right? So this R will slowly, it will gradually increase, and then it will balance this growth generation rate and the system at that condition. If the light intensity we are not changing it, temperature we are not changing it, keeping it them constant, then this two, generation rate and recombination rate, will balance each other. Okay, so in this condition, let's write down the recombination condition first. So we are taking the condition when we shine light. Okay, so when we shine light, R equals to beta into NN Tn. So initially we write, you can see that RTH, it was at thermal equilibrium, this was the condition. But now we are shining light, so now the recombination rate also changed, beta, and this N and P also changed, right? You can see that now that 0, we are not writing it, right? So that means, so NN, it defines the electron concentration for N-type semiconductor, right? This small n for N-type at non-equilibrium condition, or yeah, at thermal non-equilibrium. Equilibrium. Okay. So that's why that 0 we are not keep putting it here. And you can write it off like so, beta will be, so thermally generated electrons plus delta n. Similarly for the holes, sorry, Pn will be thermally generated holes, right, plus delta P, right? Because we have this delta N and delta P, they are the excess carriers because of light, right? Excess carriers. And definitely this delta N should be equal to delta P, right? Charge neutrality. The number of electrons generated must be equal to the number of hole generated, right? Due to this light absorption. So they must be equal. So this is our total recombination R. and total generation rate G is equals to we have GL, right? So this is generation rate due to light, and then we have GTH, right? So in this condition, we are basically generating electrons and holes, right? They are getting generated and they are also recombining with this recombination process. Now, mathematically, if you want to prove them, so what will be the net change in hole concentration?
Sir, in the generation rate, sir,
Uh-huh.
we will not consider carrier injection, sir, like biasing.
No, in this we are not considering biasing. Yes. So if you have again biasing, then there will be different generation, right? Right now we are just considering only light. When there is a again forward bias, so in this condition, of course, the situation will change and we will derive. So from there we can calculate the diode equation and all. Everything will come from there. But for now, we are just seeing a simple semiconductor piece and we are shining light on it. So in this condition, if you want to calculate the net change in hole concentration, so this is dPn dt. So rate of change of hole concentration, and we are taking N type semiconductor. So this N is will be the generation rate, right? The total G minus R recombination, right? So if you subtract generation rate with recombination rate, we will get change in hole concentration. Right now, this G has two component, GL and GTH minus R. Now at steady state, as I said, so if this condition, if you keep it for some time, then this whole generation rate or this change in hole concentration will be zero, because the recombination rate will balance it. At steady state condition, this dPn dt is equal to 0. If you put this, I mean, if you now, okay, let's give a name 1, 2, right? Now, if you combine this 1 and 2, so we'll get at steady state again. At steady state from 1 and 2, so GL plus GTH minus R equals to 0, right? So from here, if we calculate GL or the generation rate due to light, so this GL will be equal to R minus GTH, right? Right. So at steady state, the rate of generation because of light, it has to be equal to the rate of recombination minus thermal generation. I mean, intuitively also you can say this, right? I mean, the best way you can understand is the generation rate, right? GL plus GTH, total generation rate is equal to total recombination rate. It has to be true always. I mean, not always, at steady state. Okay. But when we just started shining the light, right? At the beginning, what will happen? This generation rate will be higher than this. I mean, total generation rate will be higher than the recombination rate, and then the population or the number of electrons concentration will increase in the conduction band. Hole concentration also will increase in the valence band, and then, as we know, this probability or this recombination rate proportional to this Nn and Pn, right? Concentration of electron and holes both. So this will take over, right? It will also increase. And at steady state, it will balance to the generation rate. This concept is very important when we try to understand all the light related devices like solar cells or photodiode, phototransistors, right? And later we will see for the diode that where basically carrier injection takes place, or transistors, MOSFETs. Okay, so any doubts so far? I'll just go a little up.